All right, welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules as usual. First of all, please mute yourself during the talk. If you have immediate questions, you're welcome to unmute and ask. Otherwise, please use the chat room to post your questions so that we can address them in the Q&A session at the end. Second, today's seminar is open to external audience, so no classified discussion is allowed. Finally, the talk will be recorded and uploaded to our YouTube channel. So now let me introduce our speaker. It is an honor to host Alvaro Coutinho, who is a professor in civil engineering and the coordinator of the interdisciplinary area of computational engineering and science at COPI, the Alberto Luis Coimbra Institute for Graduate Studies and Research in Engineering in the Federal University of Rio de Janeiro in Brazil. He got his doctoral degree in the same school in 1987. He is a recipient of an IBM Faculty Partnership Award in 2001, the J. Tinsley Oden Faculty Fellowship at UT Austin in 2004, the Giulio Mazzarini Academic Award at COPI in 2007, and the International Association of Computational Mechanics Fellow Award in 2012. Professor Coutinho has organized national and international conferences, training workshops, and short courses, serving in scientific committees of many conferences, including the Supercomputing Conference, the SIME Conference on Parallel Processing, finite elements in flow problems, the US National Congress on Computational Mechanics, and the World Congress on Computational Mechanics. He serves on Executive Committee of the International Association of the Computational Mechanics and in the Brazilian Association for Computational Methods in Engineering. He is a member of the editorial board of International Journal of Numerical Methods in Engineering and Computational Methods in Applied Mechanics and Engineering, and on the advisory board of the International Journal of Numerical Methods in Fluids. He coordinated over 80 industry projects, directed 33 PhD theses, and 37 Master of Science dissertations. He is an author of 136 peer-reviewed journal papers and over 450 conference papers. He was the PI of the Brazil-Europe project HPC4E, High Performance Computing for Energy, from 2017 to 2020. He is currently the PI of the thematic network in artificial intelligence for renewable energy and climate change, supported by the Rio de Janeiro State Agency for Research. Today, he will talk about enhancing data-driven workflows for complex simulations. Please enjoy the wonderful talk. Now, without further ado, let me hand it over to everyone.
Wow. Okay, thanks, Tony, for the long introduction. You could be shortened one just by saying I still play beach volleyball. Okay. Well, it's a pleasure to be here with you today. And well, you've seen my screen, and I'm glad to share with you our view on how to enhance data-driven workflow for complex simulations. The agenda for today is we'll do a quick review on the simulation workflow. Then we're gonna talk about, you'll see, how in situ visualization fits within, and how we do computational steering. And then the first question we're gonna address in this talk is how snapshot-based data-driven computations fit within this simulation workflow with in situ visualization. Then we're going to see a lot of case studies using basically dynamic mode decomposition. So there's a lot of questions. We see first, we'll ask ourselves what would happen if we compress the snapshots. What we do if the snapshots are not in the same space, for instance, coming from adaptive mesh refinement and coarse computations. And then we're going to discuss how can we mix the in situ visualization workflow with streaming DMD. Is it good for anything? I mean, let's discuss this. And in the end, if I have time, I will address a particular more theoretical issue on DMD. Should we do it couple or uncouple? And of course, we will open for a Q&A session in the end. All right. Here you see the basically simulation workflow. It starts with some pre-processing where you select parameters like the initial time step, the time interval, set tolerance, pick up the solvers, and set up and all the setup for the adaptive mesh refinement and coarsening simulation, etc. Then you stop time stepping. While you don't reach your maximum time interval, you assembly and solve nonlinear equations, you adapt the mesh and the time step, you update your solution, and then if it's time, save data on disk when required, update your time step, and move on. In the end, you have a lot of data in the disk, you're post-processing. You do the post-process, basically you visualize the data and extract relevant quantities of interest. Well, step A, assembling and solving the nonlinear equations by some, Newton-like method, is where you will spend most of your computer time. In a way, step B guarantees accuracy in space and time. And step D is where you do I/O to persistent storage. And the right, you see some solutions, some simulations coming from our group. Let's see, that beautiful one here on the top is a solution of a non-local phase field model with Phoenix. And on the right, you can see a time step varying for order of magnitude, adaptive time step varying for, several order of magnitude. And below, the simulation for a droplet impact using lid mesh with adaptive mesh refinement and coursing, and you can see, cut showing the mesh adaptivity. Many years ago, this basically workflow that is still valid. In this paper here, the supercomputer in 2010, they realized that the optimal complexity of this workflow is order of n to the power 4/3, where n is the total number of your unknowns. It's easy to realize. Let's think that you have n/3, a cube, let's say, with n/3 unknowns in each of the Cartesian directions, and you do a implicit time step with the number of time steps of order of n. If you get everything together, you get this n to the power of 4/3. It's optimal, and it is only optimal if you solve your linearized equations with an algorithm with its linear scale is linearly on time, which is hardly, to achieve. More or less, what we see here is the only way to improve this is diminishing the number of points in space and time. Okay, but there remains the I/O in persistent storage and the visualization. I mean, getting insight from your computations. All right. So how this workflow becomes put in place in situ visualization? Visualization results of running simulation. In situ visualization is basically do the visualization without the need to copy data to a storage device. Of course, it reduces the amount of data and adds to reducing traffic, I/O, and volume. And you can think that you can access more data. For instance, if you are writing to the disk at this interval, with doing situ processing, you can do more intervals. More than that, people realize, that we can do in real time the simulation exploration and the steering. Of course, it reduces latency to the first result and avoid large-scale post-processing. So the traditional workflow, you have the simulation code, dump everything to the disk, and do the visualization later. With this, now we write an adapter for this Paraview Catalyst, which is our choice for in situ visualization infrastructure. It's not the only one. And you can then produce using some scripts visualization in runtime. New applications you see in this yellow box in the bottom are two new applications from the group coming from the Ken Jensen in Colorado Boulder that are so cool. They do, they go beyond and enabling you to change your, let's say, change your domain during the simulations using these in situ tools, and also merge couple in this in situ with simulation workflow and the machine learning workflow. They're so cool. I really appreciate that so much, and I encourage you to read this. So how it works basically in more detail. The workflow with in situ visualization and steering. Here we build that on top of libmesh. You set up the adaptive mesh refinement courses setup, start the simulation setup, and then you start looping, time loop. As a couple multi-physics solver, you do the fluid solver, you do the transfer equation here. This was specialized for sediment transport. You're gonna see the application in a moment, and do if needed adaptive mesh refinement. We do the writer, and then we move to the catalyst adapter, call that catalyst adapter, and extract from the Python script and generating PNG files for visualization in situ. What we also do with this tool called DF Analyzer, the details are in this yellow box below in the slide, is that we also gather other data that allow us to interact with a lot of parameters during the simulation at runtime. We annotate some data in the database, and then we query this database if needed, and changing everything in runtime. More or less, we can see in this box here that we are annotating nonlinear tolerances, time steps, and some data needed for controlling the adaptive mesh refinement in course in libmesh. All right, how it works. Okay, this is a simulation segment run up on a channel. This is a big channel, and this is visualization generated in situ. It's a highly turbulent flow. As you can see, Reynolds number here is 5,000. And it's interesting that we have some experimental data, and the black curve corresponding to the adaptive mesh refinement and coursing simulation that you can see on the right for a longer time. And see in this detail here is the adapted mesh for this configuration. So how computational steering works. So we are some user interacting with the code, seeing when it's running, and then at a certain point at that time step, the user decide that let's relax some tolerances here and see what happens, and then he can do it in runtime and changing these tolerances, and also more adaptive mesh refinement tolerances, and see if it's okay, and the simulation progresses well. In the end, what we see here is a huge saving in computer time, and we can control this in runtime. I mean, in essence, everything is annotated in the database there where we can query, and we can interact with many parameters in runtime. So this is basically a simulation workflow with in situ visualization and steering. All this image that you are seeing, they have been produced by the in situ visualization capabilities. Right, so now come with the data-driven reduced order model. As I said before, I will restrain myself to talk about DMD, but if I succeed in my presentation, you're gonna see that several of those more computational computer science things can be applied to other ways of building reduced order models. Well, DMD needs observation from a nonlinear problem at hand, and this observation often comes from snapshots of a large parallel simulation with a workflow just like the one we have discussed. Snapshots are written to disk. Due to the gap between computing and I/O speed, snapshot generation can become a bottleneck, particularly for large simulation. DMD, as several other reducer order models, builds the reducer order model, of course, from a singular value decomposition of the snapshot matrix. So we ask ourselves, and you can see in the yellow box here, the paper that we'll be building, one of the paper we're gonna be building my talk today. We ask ourselves those two things in red here. What happens if we compress the snapshots to diminish I/O? And also, what happens when we merge DMD with the simulation workflow with in situ visualization and steering? Those are the two things we will address. The two next things I will address in this talk. Okay, so this picture here is try to give you an idea how this workflow will be merged. We have the offline phase in the HPC machine. This is a simulation with a lid mesh and a finite element simulation. And then we have two branches. This standard branch where you dump everything to the disk, but now with maybe lossless and lossy data compression using one, I will come back to this, using one floating point compressor. And then we have a compressed snapshot that have to be decompressed to be so DMD can work. And on the other hand, you have here the in situ visualization, framework and running together with the simulation that you generate PNG files. And these PNG files generated at the runtimes are fed to the incremental DMD, and then you can do the online phase in your workstation or laptop. So of course, I mean, this full order simulation take hours, and of course, the DMD reconstruction takes seconds. Everybody knows that. But most of the tools we're gonna be using here comes from the exascale computing project from the DOE, and particularly you can find this in the Alpine ZFP, which is one of the projects. So we're gonna discuss here what's gonna happen if we do data compression and how we merge the in situ visualization with the incremental DMD. As we're gonna see, we'll mix it up somehow, the offline and online phase of this of the DMD workflow. Okay, just to make a point, this is the vanilla DMD algorithm, the exact DMD algorithm. In Libron you have this. It's just to make a point that we're always going to be using randomized SVD and incremental SVD, okay? But one of the things that we have to take care is when you do large-scale simulation, the snapshots comes from those parallel computations. They are distributed in the file system. As you can see here, this is a nice picture showing you the metis partition for a 16 processor for some of the analysis we did for CFD many years ago. It's a Los Angeles class submarine mesh. We use this mesh for many CFD computations in the past. But my point here is that special care should be given to the subdomain interface data in order to arrange the snapshots. Why is that so? Because partition for computing SVD, which is basically a dense matrix, is not exactly the same the partition that when you do your snapshots are coming as a download to disk from a parallel simulation. Okay, so we have to take care of this. Right. Now let's get back to spend a bit of time talking about compressing float point numbers. Well, several state-of-the-art lossy and lossless scientific data compressor have been evaluated recently. See, this Zhao paper here called SDR bench is a bench. They propose a benchmark for scientific data reduction for lossy compressors. There's in this paper you can find many, and we selected ZFP, which is one that operates on a d-dimensional array, by partitioning this array into blocks of 4 to the power d values. Each block is compressed, decompressed entirely independently from all other blocks. Well, when you use ZFP, you can control the block's quality and compressed size by modifying 4 parameters. I will not go into details of these parameters, but at a high level, ZFP provides 5 predefined compression modes that affect these parameters: expert, fixed rate, fixed precision, fixed accuracy, and reversible. The first 4 modes allow a high compressor ratio with controllable loss of accuracy, and while the last one performs lossless compression. Why ZFP? We use ZFP well because there's a strong mathematical background. There's a paper discussing error analysis for ZFP that you can see here in this yellow box. It has been published in the Science Journal for Scientific Computing a few years ago, and that's why we adopted ZFP. So, and more than that, we adopt the fixed accuracy mode that, given a tolerance that we select, set min x per meter to this expression for longitude tolerance, which means in practice that for uncompressible floating point f and a reconstructed value g, the absolute difference of f and g is at most 2 to the power min x. Also, what is interesting is now ZFP is available as for compression, decompression, floating points on HZF5 files format using this plugin here. So it's easy to use. Right. Well, let's see what's going to happen. I come back to this problem that we analyzed in a few years ago. Is a particle-driven gravity flow in the lock exchange. Here you have a water with sediment. Here is clean water. Is basically a couple incompressible Navier-Stokes equation with sediment transport at the ratio of 10 to the power 6, Schmidt number 1, which means the flow is driven by turbulence. You can get the details for the initial condition and boundary conditions in our paper, but I'm just making a point here that at the bottom you have this boundary condition for the sediment concentration, which means that sediments are allowed to leave the domain. We assume the Bubsenesque hypothesis is valid. Particular particles have in the heavy fluid have a negligible inertia and are much more smaller than the scale of buoyancy induced fluid motion. We settle the setting velocity to 0.2. Is a trilinear hexahedral mesh with grid spacing 0.025. We're using the residual base variation multi-scale finite element formulation for the fluid, and streamline up with Petrov-Galerkin and finite element formulation for sediment transport, and we record 2,000 snapshots. The full order model is a lib mesh parallel simulation. We spend roughly 80% of the time on the solvers, less than 0.1% for the output writing, 0.5% of total time for Paraview Catalyst, and 18% for the remainder of the task. And we use mesh.io for mapping DMD approximation and modes to the original nodal coordinates. This is a snapshot of the simulation, but you can see the formation of the Kelvin-Helmholtz billows. Okay, yeah. So snapshot compression. This table here shows the storage requirement for the quantities of interest in the compression rate for these simulations. You can see for the raw data, for the ZFP with lossless compression, and ZFP with fixed accuracy for two tolerances, one more tight and one more relaxed, and we are storing the the three velocity component, UVW, the pressure, the sediment concentration, and the sediment deposition. You see that for some of those variables, we achieve high rates of compression, the sediment concentration and the deposition, and they are all compatible with the people recorded in the benchmark I mentioned before. So this is more or less what people have seen in those data sets. What remains to be seen now is that when we do this, of course, we're going to save a lot of a disk, but how this will influence DMD and the reconstructions. Okay, so we do the reconstruction. This plot here in your left show you the peak to sign noise ratio, which is a measure of how good are your compressors. In blue, this is ZFP lossless, PS and R in decibels around more than 100, which is very good. ZFP with accuracy fixed, accuracy 10 to the power -6 is over 75, which consider excellent. And for keeping three or four digits is not that good, but is acceptable. On the right, you see the influence of compression on the singular values. Well, the dashed line represents, the base with 250 singular values that we're going to be we selected for the DMD reconstruction. We see a deviation on the singular values for when we do, when we do a very aggressive lossy compression, but the singular values agree with each. You see, lossless and no compression are on top of each other, and we do a less aggressive. We have a very good match until, let's say, 350. So we're gonna see what happens when we do the reconstruction with 250. A singular with the basis built with 250 modes. Okay. Oops. All right. But before that, let's see what happens with the DMD eigenvalue analysis. For the loss compression for 10 to the -6, you see that apparently all the eigenvalues are okay. We have some small discrepancies, and when we do zoom in this box. But however, for the more aggressive compression, we see more discrepancy in the eigenvalues, and of course, it will affect the DMD reconstructions. So in this table here, you see the Frobenius norm relative error between the approximated and original snapshot for this problem, considering a basis of 250. You see the Frobenius norm are okay, more or less, when we do no compression or lossless compression or this with a 10 to the -6 accuracy. They are more or less of the same order, but they are twice as big when we do a more aggressive compression. This picture on the right, you can see the absolute error between the DMD reconstruction with a basis of 250, with a basis using 250 eigenvector from the lossy compressed data with the 10 to the power -6 compression and the original snapshot for the sediment concentration at this time. So you see very small absolute error, but this is not enough. Let's see more other measures. In the graph in your left, you see the relative error in time measured as the difference between the reconstructed solution and DMD solution. You see the norms, and you see that this error is very, when you do no compression, in orange lossless compression, in green lossy with the 10 to the minus 6 tolerance and the more aggressive compression. We see a very good error. The lossy and lossless are more or less on top of each other until that time, and there's some divergence afterwards. But overall, the errors is still low, below 10 to the minus 2. On the right, you see the time history of the relative sediment mass error for all cases. They are very good, and when you do a very aggressive lossy compression, decompression, you see that there are some oscillations, but overall, the mass is very well reconstruction. Finally, people who do these simulations, there are some quantities of interest, global quantities of interest that they always look. One is the front position over time, and for this, which is basically how you compute where is the front over time, you can see there's a very good match, no matter what you do, using raw data for the world model, raw data from the simulation, and all the compressing all the snapshots. You see for this global quantity of interest, you're on top. And also from the sediment mass time history, that's you see the same thing. So it appears that compressing snapshots by using with keeping some accuracy, good balance between how much you're gonna compress and decompress is a good idea. By the way, the decompress time for the DMD is negligible. Okay, all right. So let's see what happens when we have snapshots coming from adaptive mesh refinement and coursing. When you do adaptive mesh refinement course simulations, the meshes we have, they have, of course, a different number of nodes, numbering and nodal coordinates. And it can also lead to different mesh topologies and structures. For instance, you see 3 levels of refinement, and then you see, these meshes, of course, they don't live in the same space, and you can have something like this, a hanging node, which is constrained by their neighbors. Or you can have situations like this, mesh 1 and mesh 2, that they have the same number of degrees of freedom, but different topologies. We circumvent this issue by considering L2 projection of the numerical simulation results for different meshes into a reference target mesh. So there are some issues here. Okay, the choice of a proper method to successfully project functions in different finite element space is not a trivial task, and particularly because conservation may not be satisfied. If you go to the literature, there are several works in addressing this issue. However, we have to bear in mind here that mass projection for us to build a DMD snapshot, they occur as a post-processing phase after computing the adaptive mesh refinement course solution. Therefore, it cannot lead to cumulative errors. So projection doesn't accumulate error. There's another issue here is how much the snapshots will retain from the regional accuracy of this adaptive mesh. So what we found out that we need to choose a reference target mesh with a characteristic length equivalent with existing in adaptive meshes in order to avoid major accuracy losses. So how it works. Let the solution on the donor mesh be given by this expansion, satisfying this L2 projection here in the proper space. And of course, L2 is defined by the target mesh, and interpolant here, U subprod is the optimal interpolant in this L2 norm from this space. So we computing the L2 projections, these orthogonal projections, is defined in the following linear system. And you can solve this for U proj, where M is a standard mass matrix for any finite element code, and P is a projection matrix. We prove a theorem in this paper down here, is that if every degree of freedom of the regional mesh is also a degree of freedom of the reference mesh, then the matrix P is full rank, right? Which is a very tough requirement to be met in practice. But we find out that having a reference mesh representing defined scale is enough for practical purpose. So this algorithm, snapshot projection, will work like this. We have an input, the finite element solution, considering adaptive mesh refinement courses, and the output are the projection solutions. So for each observation time step, you apply the L2 projection and stack the result in snapshot matrix, or output the projection solution to this, compressed or not compressed, doesn't matter. On the right, you can see here is the, it's a simple exercise. We project the solution, and this is adapted mesh, and this is the infinite norm, this is 1. When you use this mesh represented finite scale here, the projection is very good. Or if we project in a totally unstructured mesh, more or less keeping the same scale, we have also a very good error, right? So let's check out how it works in practice. Let's examine right now the problem of a 3D rising bubble, which basically a couple Navier-Stokes equation. Sorry, just a second. Is a couple Navier-Stokes equations with a convected level set, where we consider surface tension with a continuous surface model. The details are in the paper in this yellow box here. This is the initial condition, and no slip boundary condition applied to all boundaries. The computational domain is this box here. We're going to have grid size in this interval. There will be 240 time steps. This is a time step, the bubble radius, the initial bubble position, the properties, and we consider gravity like this. So first thing is how this idea of looking at projected meshes works. We can see here in this plot the adaptive mesh solution, the projection for this time step on a coarse mesh, an intermediate mesh, and a fine mesh projection. And in the table here, you can see how costly is the projection. You see, well, for fine mesh, the projection cost is negligible, and its projection like this L2 projection is available on this either is part of a libmesh, is part of Phoenix, so projection is not an issue. The issue here is how the solution becomes when you really do take a look on the solution quality in these projected meshes. So you see some quantities of interest for this problem. This is the volume of the bubble, the sphericity, the rise velocity, and the center of mass. For the for the simulation with adaptive mesh, and the output in with the coarse, intermediate, and fine projection. Of course, the coarse the solution projected in the coarse mesh is good for nothing, but for the intermediate mesh and the fine one, these quantities are all okay, which it gives us a good indication that projection can give you snapshots in the same base in the same space. So we proceed to do a DMD reconstruction with the projected meshes. Here is basically the relative error for the reconstructions. And we see relative error here. And this is the training. And then after the training, you see the trainer the error increases a bit. But we have in all this, DMD are good. And for the coarse mesh is not that good, but you can see in this two slides here that the bubble shape at that for the sign during the sign reconstruction, which is at the end here of the training, and for the prediction within the last step is more or less okay, and we can see some really oscillation for the coarse mesh. And of course, in this table here, you see for several ranks, DMD reconstructions, and then you see the relative error. Of course, if you increase the rank of the reconstructions, the error diminishes. But you have you see astonishing, a very very nice speed ups. So it seems to be a good idea to have all the snapshots in the same space by projecting the solutions. So let's see how DMD performs for the quantities of interest. Again, I see volume, sphericity, the rise velocity and center of mass. And I believe this is for using for using the reconstruction with 60 vectors. And you see again, DMD reconstruction with the coarse mesh is good for nothing, but for the fine and intermediate projection, they are of value. I mean, you can do it without any problem. Okay, so let's now see if how this idea of mesh projection, of having all the snapshots in the same space works when we merge this with data compression. So by using only the finite projected mesh. Here is the timeshare is on the offline phase is 90% for the solvers, less than 1% of the time for output writing, 1% for Paraview Catalyst, 30.3% for the bubble position projection, the reference mesh, and 80% for the remainder workflow components, with including all the stuff you need for adaptive math refinement and coursing process in libmesh. For this specific problem, you can see here, you see a view of the for the time t.25, the adapted mesh with the velocity plots, and the corresponding projection of the level set or the bubbles position at the fine mesh. Note here that we compress both the level set field on the adapted mesh and the level set field on the projected mesh. The projected mesh contains more nodes and elements, and given that there's the same mesh for all snapshots, of course, it enables the use of DMD. All the other fields are stored in their original adapted meshes. So here again, we see the table. We can see the three velocity components, and then the compression rates, the pressure, the level set, all this in adapted mesh, and the level set in the projected mesh that will be used for the DMD reconstructions. You see that we achieve some, less. We can discuss it later, why we achieve less than in the other case, but still good compression rates. Okay. And again, we do the same thing. This is the peak to sign noise ratio, and we see that for ZFP, the lossless compression, and the same, accuracy level for ZFP compression. Here we don't see, more or less the the lossless and ZFP recurrence 10 to the minus 6 is more or less on top of each other, and the quality of the more aggressive data compression is not that they still have a good quality. This is somehow reflected when you look at the singular values. For a basis of 20 singular values, we have here all the singular values when I'm gonna do the reconstructions with 20 vectors, but they're all more or less on top of each other. And if we look at the Frobenius norm, relative norm between the approximate and the original snapshot for a basis with 20 vectors, we see that they're more or less the same order of magnitude. And again, the DMD eigenvalues, if you look at them, the raw data, the lossless, and the two, compressed and decompressed with different tolerance, they are all on top of each other, more or less reflecting what we see in the singular values. Okay, so this is the relative, on the left, the relative error in time for the DMD reconstruction with 20 vectors. We see that that's okay. The relative error in time is bounded, 10 to the minus 2. And the time history of the bubble mass, which is very, very similar with what we got with no compression at all. Right? So far we have been, seeing the effects of data compression and how to handle snapshots with coming from when they live in different spaces. We do it by compression, and now we're gonna see what we do when we merge DMD with in situ visualization. All right, some more water. And I'm gonna do faster here. We see, we have seen the integration between libmesh and Paraview Catalyst, and this is provided by adapter, which is implemented when on one of the Catalyst APIs. More or less, we couple libmesh with Paraview Catalyst, and we produce PNG files that will feed streaming DMD. The adapter invokes Python scripted, which is ported for the Paraview user interface, and the adapter involves these processes: initialize, coprocess, and finalize, which are methods to invoke pipelines defined in this Python script. The data structure from the simulation code is accessed in memory, in situ, and they are mapped in the adapter using the API for Paraview Catalyst, and Catalyst using VTK's data model to perform the data structure mapping. The usage is simple. We output PNG file every X time steps and write data every KX time steps, with K much more than 1. And PNG files are ingested into the streaming DMD algorithm, which is on the right. I'm not going into details. I'm just saying it's very similar to the incremental SVD you find in Libron. However, it's tailored for receiving PNG images. We use this Python package OpenCV for handle image and scikit image for computing metrics. And the images are converted to black and white before processing, and pixels are handled as nodal values in the snapshot matrix. This is to make things simpler. All right. So what we do is the streaming DMD of the lock exchanging computation. We use Paraview Catalyst to generate images for us at the mid-plane of the lock exchange problem. PNG files have only this amount of pixel, which accounts for 153 megabytes. We store all 4,000 images. We store for every time step. And this is DMD reconstruction for a base with 250 DMD modes. Okay, visually there's no difference between any of this. The full order model image, the in situ visualization image produced with online with the Paraview with the full order model data, and the reconstruction with the Paraview, same image with the DMD reconstructions. However, we have to bear in mind that assessing accuracy image needs more different metrics. Why? We use this structural similarity index, which is computed like this. It is very standard. I just would like to point out that if this is the original image, and this is two compressed and decompressed image, the PNG, maybe you have the same MSE, but this metric tells you that the image on the right is much better than the middle image. So when we handle everything as images, better use these metrics in order to assess quality together with our standard more mathematical error analysis. So for the Locke-Stand problem, what we get when using the streaming DMD, this mark here is the mark that we have 250 snapshots, and all the reconstruction keeps going with this 250 snapshots or PNG files coming in. And you see this metrics as close to 1 means that the images are very good, and you see by the scale that this is true. The DMD reconstructed images are very good. And this is also reflected in Frobenius norm in time, and also in the relative error. They all tell us that the reconstruction with this using the images produced by the in situ visualization, DMD reconstructions are very good. What we got when we do the same thing on the 3D rising bubble problem. Well, now we generate black and white images at the bubble midplane. PNG files have only this, so we have 3 megabytes for storing all 240 images, and we do the reconstruction with R60, and you see the Paraview Catalyst image, the DMD reconstruction, and so on. We see here in the end, after the training, the prediction phase, that DMD does not do a good job in the reconstruction, but is more or less, we knew that when we observe the reconstruction in the bubble, perhaps is because the boundary conditions we apply here is a no-slip boundary condition, and this is reflected in this other metrics. This is the structural similarity index for the reconstruction images from the bubble shapes is still good, and we see a degradation here in the end. Again, this is when we start to have the 16 started reconstruction, the Frobenius norm is not that good, but still tolerable, and the error is growing as we saw before, but it's still acceptable. Okay, and we have 5 minutes. Should I continue or stop here and go to the Q&A? I can go very quickly on this. Basically, what do you think, Tony?
Yeah, I think it's up to you. We are pretty flexible in the schedule.
Okay, I mean, I will jump to this because it's a more theoretical work. Suppose we have a PDE system that we have this vector here, and this is a kind of a multi-compartmental system, when N is a nonlinear operator that defines the interaction between an I and J compartments. Of course, this equation is equipped with BCs and in initial condition for each compartment, and depending on the type of the equation, we can use Galerkin, Petrov-Galerkin, a variation mode scale for spatial discretization. The question here is what we do with DMD reconstruction, each degree of freedom or each compartment separately, or but stack all of them like this. and do the DMD for the couple approach. Of course, this will demand more memory, but of course, and the reconstruction follow this expression. But see which one is better. Right. In this paper below, we have a mathematical analysis, and we have proved three theorems. First one is for a compartmental dynamic system such that we have this conservation. The exact DMD reconstruction utility here also, is conservative. The second theorem says that for problems with some subset of a compartment satisfies the hypothesis of theorem 1, the theorem 1 also holds for the DMD reconstruction in this subset. The third theorem says that for a compartmental problem which satisfies the hypothesis of theorem 1, if we have additionally that this is, this condition here that the compartments are positive or zero, and DMD reconstructions are also this positive or zero at all positions in time, then we have the L1 error is bounded for all time. Some remarks on these theorems. This non-negativity hypothesis on utility for theorem 3 is hard to say that it does hold in general, and these quantities may become negative. But what we see in practice that this assumption remains satisfied for many problems, at least for a moderate period of time after the end of the training period. In such a regime, we may expect that the error bound given by theorem 3 to hold, preventing the blow-up of the error. Moreover, if one wishes to perform DMD on an augmented variable space, let's say we have one U2, these two compartments, and a nonlinear combination of those, we would expect that this conservation will hold in the DMD reconstruction despite the presence of the nonlinear variable. The mathematical details is on the paper, I will skip this, but let's see how it works. This is a system of reaction diffusion equations, which basically is a special temporal delay and susceptible infector. It's recovered and decisive population for simulating spreading of disease. S, as I said before, S stands for the susceptible compartment, E for infected, R for recovered, and then D for disease. The sum of all compartments, with the exception of the diseased population, is represented by the N population with the total number of living people. The beta are the transmission rate, gammas are the symptomatic recovery rates, deltas are mortality rates, and here is are the diffusion tensors of the different population groups, and the sigma incorporation, the lag effect presenting between the time of infection and the developed symptoms. And the model seeks to, and it seeks to model the delay observed in practice when new restriction of other measures are introduced. The details of the model is the paper in the yellow box below in the slide. All right, the model works. This is in pink. You see the number of diseased population against what was measured in the state of Georgia in the US, and we observe an excellent agreement for the total population for Georgia for this model, and this is the evolution of the infected compartment I for the Georgia simulation of different phases of the epidemic. Day 1, day 1 month, 4 months, and day 150. Of course, the outbreak was more severe around the Atlanta area, but we have other hotspots as well. Well, how DMD performs on this? Well, we're gonna see that the variation of the mass has to be conserved, and we see that if we do DMD reconstruction in an uncoupled way, we don't see any conservation, But however, if we do the DMD reconstruction with the coupled way, we see a very good conservation even beyond the training period. And this is the infected compartment, 5 days after the end of the training period. And we have a very good agreement between the full-order model and the DMD reconstruction for the couple, using the couple way of doing this. Okay, and this is the error analysis. And for the Georgia simulation, this is how we compute the error. And for the different compartments, susceptible, infected, recovered, and disease, we see that uncoupled DMD reconstruction fail for several compartments, giving unacceptable results. In contrast, the coupled DMD formulation, reconstructs the dynamics even after training, and provides reasonable extrapolation for a 3-week interval, which is very good for the problems of epidemic prevision. And it more or less confirms what the mathematical analysis have predicted for us. So final remarks and discussion to end, and finally go to the Q&A. Some more water before I start my final remarks. Okay, we have seen that lossy compression diminished the snapshot persistent storage requirements and contributes to decrease I/O. DMD approximations using decompressed data may lose accuracy depending on the singular values threshold. If loss data compression changes the singular values before the truncation level, DMD eigenvalues may change too, and you're going to expect not a good reconstruction. We have observed that decompressing the snapshot does not increase computational effort during DMD approximation. One thing I'm pretty sure, data compression is here to stay. You guys in the labs are putting a lot of effort on doing this in compressing scientific data sets. So is there, and please use it. There are other options in ZFP that remains to be explored. I'm not claiming that we did the best job. We just said, oh, okay, look, data compression here is good, but we have to, to do more computations and explore more. Now, of course, there are other scientific data compressors worth taking a look, like SZ, MGuard Plus, etc. And one thing that is important for you guys in the Liberon community is I believe that any method based on snapshot can benefit from data compression. It's more or less obvious, this thing, but I never see many people using, scientific floating point compression in this method. And we could expect more savings for outer looping computations. You see, when you do, of course, if you do parametric studies that will generate much more data, well, when you do more compression, you do more and more savings. So, by using floating point in compression for parametric studies, can expect much more savings. Again, using image data for DMD approximation presents accurate results considering the presented metrics with notable storage reduction with promoting simple data transfer. Another thing is projections of fixed mesh could not be the best way of dealing with the snapshots in different spaces, but it's simple. Why? Well, L2 projections is embedded in many existing codes. Open source codes like libmesh, Phoenix, and I believe in many of the simulation codes available at DOE, we have this projection already implemented. Our experience shows us that the hint is, if possible, select a fixed mesh containing approximately the smallest scales obtained in your adaptive mesh refinement and coursing solution. In situ visualization turns the offline and online phases blurry. They are somehow mixed together. If it's possible to generate in situ visualization image target to the problems Q quantities of interest, short-time incremental DMD prediction can aid steering tasks at runtime. You see, if you're receiving a bunch of images and then doing a DMD or some run reconstruction, you can somehow predict at runtime what's gonna happen with your simulation and then take action using the user steering capabilities built in your simulation codes. Again, I think that image metrics should complement our traditional error analysis. Look, you're using images right now, so you have to take a look on image metrics. In the end, for comportamental PDEs, we have seen that our theory and have been, in numerical experiments have shown that coupled DMD should be preferred. Yeah, that's the team. Myself, Alessandro Reali, our colleague, and Marta Matoso from computer science. She helped us a lot on the steering part, like Patrick Valderiez, Alex Vigri, which is now at CDC, Malu Gravi, my former student, Jose Camata, also my former student, Adriano Cortes, my former student, Gabriel Barros, who did a lot of works in DMD. He's finished his PhD right now, but a machine learning company in Brazil already hired the guy. And Victor Silva and Renan Souza also helped us a lot. Victor Silva now is at Apple. And Renan Souza is your colleague in Oak Ridge. You can talk to him about this steering stuff, that he knows a lot about this. This is our, I would like to acknowledge our supporters, and that's it. Thank you so much to be here with me today, and thanks for your attention. I'm ready for Q&A.
Yeah, thanks for the wonderful talk, Alvaro. Yeah, I'm particularly impressed by the comprehensive workflow on like different simulations, different applications, and like the interesting error analysis, analysis on the data compression. So let me see. I don't think we have a question in the chat room yet. So probably I can kick off with one question. So I'm curious about like what to do. What do you think about like incremental DMD in the parametric case? Like we have, I know you do the sedimental transport as an example. I think you have one particular Grashof number and the Smith number, right? So
yeah.
So if we have like multiple of them, maybe we can do it in like simultaneously, and we build the incremental SVD simultaneously. So do you think like you will have giving a new testing parameter another unseen problem in terms of the Grashof and the Smith problem? So how will you like do the DMD prediction there?
That's a very good question. You see, I think there is a strong potential if you figure out the problem with the situ visualization is figure out, the script in order to produce the images, right? If you have a parametric, let's suppose that you are doing parametric exploration and we have a lot of jobs running in a supercomputer. And for each one of them, you are downloading, for the same point of view, more or less with the same mesh, you're downloading images. I can think that you can do, you can show that this database of images and doing incremental DMD, we can show a new parameter and see if the reconstruction is okay. I think this is a test worth doing, because you're gonna check out in runtime what we're gonna happen in this new parameter and figure out if we have to start a new simulation. I mean,
yes,
it's not good. It's an indication for you. Okay, let's put more. Let's start simulation with new parameters.
Right.
This is a clear application of this idea.
I see. Yeah.
Our group was more worried at that time in order to complement what we have been doing in steering. in order to, doing the streaming DMD to predict what's going to happen and then intervene in the code. But what you have said is really, I do agree with you. If you figure out for, let's say, the same configuration and several parameters, and you have the images, you just expose your streaming DMD to this new parameter and see if it's worthwhile to increase your parameter space or not.
Yeah, that's right. I think we can talk more on this matter because the LibRound team, we are also looking at like having automatic like error indicators for like finding the parameters that we have to like build more snapshots for like having a better universal estimation in the whole parametric domain. So yeah, maybe we'll learn from your experience, and maybe we can also talk about our work in the residual-driven like sampling methods there.
Yeah, Tony, that's absolutely right. I mean, you could use, for instance, KNN or any other method to combine all these things, or a neural network to, to do this. But that's absolutely correct. I think the team is, you need to do that. It's worth doing.
Yeah. So I may ask one more question.
Sure.
So it is like I don't have a clear idea about this, but I mean, in the whole talk, we mainly work in talking about these simulations. But so I'm thinking about like a a decision-making process or a like multi-query problem. So usually we want to mesh the simulation with some kind of observed data, and there are some noise in there. So do you have like any comments on some insights on how the noise level is, I mean, related or affecting the like the ZFP compression level that you should choose in the DMD?
That's a very good question. You see, yeah, those things here. Peak signal to noise ratio is a measure. The guys who wrote this this paper I quoted here, where? Yeah, those guys. Those guys here for the benchmark, they tested, and there is let's say a bench. They propose a benchmark with all this compressor, and those guys, they are one of the quantities that is new to our community. At least we don't tell much about this. Is this peak sign noise ratio, and tells you how this noise generated by the compression affects your snapshots in the end. When you decompress, how it is how your snapshots will be affected. So I mean, compressing and decompressing by something like 75 to 80 or is considered good. And this comes from those image guys. You see, when we were doing this, we went to the image literature. If you take a look on the paper where we did that, we quote a image book. This is something new for us CSE guys, but it's bread and butter for the image guys. So I'm saying that that's why I said in the end that there's more on data compression, and that's why we choose ZFP in the beginning, because there is a strong mathematical background and error analysis for ZFP, as well as for the other compressor. Is one. MGuard Plus. There's a strong mathematical background in this MGuard Plus. So it's worth I mean, it's hard to say at that point which one is the best one. But again, I repeat what
Yeah.
I wrote here. Data flow compression is here to stay.
Yeah.
So it's something that our community has to start coping with, and our experiments just say to us that, oh, okay, it's not that bad. We can cope with this because we're gonna start receiving data that are only available in the compressed form.
Yeah.
Simulations are too big.
Yeah, I totally agree. Like especially it's interesting. Like the ZFP, they are actively researched within the class of RNL, and we will probably we will certainly want to like incorporate these techniques in the LibRAM that we are developing to like
Yeah, I mean,
this.
they are, for instance, ZFP is part of the HDF5. There's a plugin for this.
Yes.
And I'm pretty sure that you guys in the labs don't just go for the XScale project guys and talk to them. They will be readily available.
Yes. Okay.
Okay.
Yeah. So let me ask once more. Are there any more questions from the audience? So if there are no more questions, let's thank Alvaro again for sharing his excellent research with us.
Okay.